Hello there and welcome. My name is Hafsa Liksari and today I will be talking about the dissertation titled The Evaluation of Genome Data Alignment Algorithms. The aim and the objectives. The aim is to evaluate the various computational algorithms such as the tools BWA and Bowtie2 for genome data alignment. The objectives are to understand and critically review the existing algorithms for the genome data alignment, to conduct a manual genome mapping using BWA and Bowtie2 alignment algorithms, and to test BWA and Bowtie2 alignment algorithms against factors such as accuracy and memory used. The last objective is to analyze and critically review the results from the previous objective. So what is the Bowtie2 algorithm? The Bowtie2 has the ability to index the genome with the FM index, which is based on the Burrows-Wheeler transform, to keep the memory footprint small. The human genome has a memory footprint of around 3.2 gigabytes of RAM. Bowtie can support the gapped, local, and paired end-to-end alignment modes. The multiple processes can be used in order to simultaneously achieve greater alignment speed. Below an example is of what the Bowtie2 aligner looks like. The Burrows-Wheeler alignment algorithm, according to the BioBWA SourceForge.net 2018, BWA is a software package for mapping low divergent sequences against a large reference genome such as the human genome. This shows an encoding example which is produced by me, the researcher. The big O notation. The big O notation is used in the world of computer science to describe the performance algorithm or the complexity of an algorithm. The big O specifically describes the worst case scenario that can be used to describe the execution time required or the space used. So how can the big O notation be applied to the BWA and Bowtie2? When comparing the two algorithms, some of the most important factors that should be taken into consideration would be the time and the space that was used whilst running the programs. Below is previous research of authors that have compared how BWA and Bowtie executed in terms of time and how much were paired. So in the results section, the first experiment was to manually map as a human expert. This here shows the results. There were a total of 27 mutations from the 20 reads that were mapped using the reference genomes. The mutations have been circled in red since they don't fit in the reference genome pattern and therefore need to be highlighted. Some of the reads had more than one mutation. However, the researcher knew if the reads were mapped elsewhere on the reference genome, there will be more than 2 mutations. This is manual mapping using the Bowtie2 algorithms. After mapping the genomes according to the Bowtie2 aligner, there were a total of 15 mutations, the 20 reads that were mapped using the reference genome. The mutations have been circled in red once again. These here are the reads and this is the reference genome. Going to the Use Galaxy website, the first thing that the researcher has done is search for Bowtie2 and then using the pasted entry, which all the relevant files have been uploaded onto the website, such as the reads and the reference genome which has been built. The second, these are going to be kept the same, and then from this drop down box we would use a genome from the history and the build index and then selecting the appropriate file that has been uploaded, and then everything else is kept the same and execute. The same thing now would be done for BWA. Once again we're using from the history and build index, we'd select the right file, and instead of paired we would select single, and then everything else is the same and execute. So these are the galaxy results for Bowtie 2 after it's been executed. This will then show, and this is what the results are now. It shows that there were 19 reads that Bowtie 2 recognized out of the 20, and 5 reads were not mapped. On the reads, the flag was 16. This shows that the read mapped to the reverse strand of the genome. The Bowtie 2 galaxy outcome. The Excel sheet has been made to show how the Bowtie 2 is mapped to reads using the Galaxy website. Although there's 6 reads missing, there were 13 mutations highlighted above. One thing that was interesting, one of the reads that were TTTTG have then been reversed to GTTTT in order to fit with a fewer number of mutations. And then the accuracy was calculated, and from here the total is 10. Once again, the accuracy is being calculated by comparing how the human expert would map, and then given a point if the reads were mapped in the exact same position. These are the results for the Burroughs-Wheeler aligner. Once again, there's the 19 reads showing from the 20 reads. There were 5 reads which were not mapped, and this is clear because they're at position 0 and the flag is full. The results are now mapped on the Excel sheet, and it's clear that there's now 12 mutations, even though there were 5 that were not mapped, 6 reads that were not mapped. Once again, the accuracy is being calculated for the Burroughs-Wheeler aligner, and the total is 11. Findings and analysis. It's now clear that BWA has taken the lead in terms of accuracy, scoring 11 points, whilst Bowtie 2 scored 10. And in terms of storage, once again, BWA required the least amount of storage, only needing 813 gigabytes, while Bowtie algorithm used 863. In conclusion, the aim of the research was to evaluate the various computational algorithms, such as the tools BWA and Bowtie 2, for the genome data alignment. This research has found that BWA has taken the lead for being the best tool out of the two in terms of memory and accuracy. When dealing with small reads against a small base pair reference genome, the complexity big O notation for memory was BWA, as the algorithm required the least amount of memory. BWA has also taken the lead for having a slightly higher accuracy rate when compared with Bowtie 2 in this particular research. One main limitation of this work is that the researcher have only used limited data sets. This can be extended by using a larger data set and potentially with a real human data set or a real bacterial data set to give a better comparison. Thanks for watching.